In this video, we're going to go over the swinging objects post-lab or the net center force model post-lab. All right, so let's begin. So that everyone's on the same page, I'm going to do a quick little sketch of our scenario. You should already have this in your pre-lab, but that I'm going to call this M sub S as my swinging object, and that swinging object was attached to a rope, and that rope was bent down like so. And just so you know, whenever your rope bends like that, often at 90-degree angles. The reason for that is what we call a pulley system. Now, usually what we think of a pulley is like a rotational wheel, but whenever something bends a string like that, think of it of almost like a pulley type of scenario. Okay, and the pulley there just changes the direction of the force. And here we have a hanging object. We can call this M. I'm going to call it capital H. And then we had the radius of the string right there. And this object is swung around and around in a circle, and hopefully you didn't hit yourself in the head. Okay, it's went around and around and around and around in a circle like so. Okay, and it was supposed to swing in a flat perpendicular plane, but illustrative wise, I'm drawing like that. Okay, so with that out of the way, let's go to our notes. One of the graphs that you had to make was a velocity of the object and the radius of the object, the V versus R graph. And so when you plotted your V versus R, the generalized shape that we got, or the pattern that we got, was something that looked like this. If you use the formula, or not the formula, the worksheet at the beginning of the year, you would have known that you got to linearize this, and we get a straight line like so if you square the velocity. Now here's the important part. At this point in the year, we need to know a couple of things. One, slope is very important, right? More importantly, linearized slope is important. But the reason why the linearized slope is important is because here the slope is constant, meaning that your ratio of your rise versus your ratio of run doesn't change. So if your slope is constant, this idea here, this constant for us in a physical real world sense, whatever you kept constant in the lab is represented in your slope. And so for us, for the V versus R, it was a swinging object. We didn't change that. The hanging object, right? We didn't change that object. But more importantly, the weight of the hanging object, so mhg, that was all kept constant. So the slope right there must have these elements in there, the values. All right. Now, in terms of the relationship, we found that V squared is directly proportional to R. Okay, so the hard part about this unit is really trying to make sense of why certain things happen when you move in a circle. Okay, and so what I like to do is I always like to imagine us driving around in a car. So there's a couple of roundabouts right outside of our school, and you know if you're at a different school and you're watching this, you think about just like driving around in a circle or like a exit ramp. Okay, so the idea of this relationship here, or even this relationship here with this graph, shows us that if there's a smaller, tighter circle, right? A smaller, tighter circle, and I'm using the word tighter here very loosely in a very everyday kind of language, right? A nice small circle, you need to drive slower, okay? And that shows us here, right? So if your radius R here is nice and small, you have to drive nice and slow. But if you have a nice big radius out here, you can drive pretty fast. Okay. Now the idea behind this phrase right here is so that you don't fly off the road, and that'll be bad. And if you're in a Jeep, this is especially true. If you drive too fast around a circle in a Jeep, you'll tip over. But you know, for all the other cars out there, this is also true. If you drive too fast, you actually run the risk of having your car fly off the road. Okay? And fly, not as like an airplane, but in a sense of a car. All right, so that's one of the relationships. And the other one that we looked at the relationship of the velocity of the object and the hanging weight of the object. Okay, so we changed that. And the relationship we got was something like this. Ooh, oh, well, would you look at that? It's the same relationship as before in terms of the generalized shape. So we get a line that looks like this. So once again, you got to think about the slope. Your slope here is constant. So the constant slope must represent whatever we kept constant. And I believe this is the radius of the circle was kept constant. And the hanging, or excuse me, the swinging mass was kept constant. Okay, so those were the things that we kept constant for this graph. All right, so once again, let's try to make sense of this graph here. So when you're driving around in a circle, the reason why your car doesn't go flying off of the road is because there's a frictional force between your tires and the road. Um, and that frictional force, like if we're using an analogy here, is what's represented here in this F. Now, in this lab, like that wasn't the frictional force that we were thinking about. That was a hanging mass. But if we're to use a real life analogy, okay, when you are going around the roundabout, it's that frictional force that keeps you within the circle. So what this shows us is if you go fast, okay, so if you're trying to like zip around the circle, you need more force. You need more force to keep your tires on the road, right? So if you go super fast, boop, 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 you're going to need a lot more force there, right? Versus if you go pretty slow, right? You don't need a lot of friction to keep you on the road. Okay, so remember the force that allows you to stay in put is the force of friction, and depending on the class, we'll actually go into what the type of friction actually is. Is it kinetic or is it static that keeps you on the road? Ooh, future talk. All right, and the last relationship. This was the trickiest one, and once again, talking in the future. Not sure if we did this in class yet, but the last relationship is velocity versus mass. And this one is a little bit tricky. So for this one, when you plotted it, we should have gotten data that looks like this. Okay. Yeah, like this. And this, by the way, is the swinging mass. Okay. Um, and here's a tough part. When you try to linearize this, the first time you try to linearize it, you go to the worksheet and you're like, oh, okay, that's just 1 over m, right? And so if you plot it like this, you actually just change the shape so that you get something like that looks like this. But that's okay, because the previous two graphs look just like that. Because the previous two graphs look just like that, we know exactly what to do. We just got to square the y. And then when we do that, we get a nice linear curve. Now, depending on how good the data is, we may or may not have gotten something that looks like this, but in a theoretical sense, this is exactly what should have happened. Okay, so if we were talking about the things that were kept constant, the radius was kept constant, the hanging mass's weight was also kept constant there. Okay, so back to the car analogy, you're going around the roundabout. What does this mean? So let's take a look at this graph here to really identify. So this shows us that the more massive your car is, okay, if you're going around the roundabout, you got to go slower. Okay, so for example, like big trucks or like semis, right? Trucks or semis that go around the roundabout or like a highway exit, okay, they have to take the turn slow. Okay, they have to. If they don't, they run the risk of sliding off. Versus if you have a tiny little car, right? If you have a tiny little car, I'll do that in green so they can make a distinction, right? If you have a tiny little car right there, small cars can take the turn quicker. Right? You can go a little bit faster as you go around the roundabout if you have a tiny car versus a massive truck without the fear of tipping over. Okay. Okay, so those are the three relationships. Oops, I don't think yeah. So let me just write down the relationship up here. So go back to your papers. This is a directly proportional, v squared is directly proportional to f. And for this relationship here, we can say v squared is directly proportional to the inverse of m. Okay, now we got to come up with a generalized formula And the general mathematical formula shows us that v squared is directly proportional to r, v squared is directly proportional to f, and v squared is directly proportional to 1 over m. So if we set all of these equal to each other, we can say that v squared is directly proportional to f, which is directly proportional to r, which is directly proportional to 1 over m. And of course, all of these being multiplied with each other. So the formula turns out to be v squared is equal to f times r over m. Okay, so this is the generalized math formula that we got for this lab. However, we won't be using this form at all. We'll actually be using the form in the terms of force. So I'm going to rearrange it, and this is what I need you to start using. F is equal to v squared divided by r times m. Okay, we're separating all that. And in the next video, I'll go over exactly why I chose to separate. So that's a generalized math formula. Okay, that's that. Watch the next video so that we can go into a very in-depth analysis of the center force model. Bye-bye.